Hi there, I'm Nishant Gadiyar and I'm a Distinguished Staff Fellow at the Oak Ridge National Lab. Welcome to my ECCE 2025 presentation on electric machine torque density enhancement using spatial harmonics. This work was performed during my PhD and postdoctoral research at the University of Wisconsin-Madison, and the paper is co-authored with my advisor, Professor Eric Severson. So in this presentation, I'll first present the background and motivation for torque enhancement and then highlight the key contributions. This will be followed by design space exploration studies on two different electric machine families, the radial flux machine and the axial flux machine. We will then experimentally validate our findings and present key conclusions. Electric machines for electrified off-highway vehicles, that is excavators, mining equipment, agricultural equipment, and so on, require extremely high torque density because these machines are conventionally using hydraulic actuators which are extremely torque dense and rugged. So the electric machines will need to be competitive in terms of torque density, and they also need high torque-to-rotor inertia ratio so that the response time could be really fast. And using harmonics to increase electric machine torque density has been studied in literature. However, it is not well explored. There have been a few publications, and the common theme is that you need to use multi-phase machines. And in this work, we are using the multi-harmonic winding design method, which I developed as a part of my PhD, and it is published in the Transactions on Industry Applications, reference 4. And the advantage of this method is that we do not need additional rare earth permanent magnets for increasing the torque density. So this work really investigates the use of spatial harmonics to improve electric machine torque density, whereas in literature, there are time harmonics and spatial harmonics, and the separation between them is not very clear in harmonic torque density enhancement literature. So the key contributions of our work are that we develop the principle and quantify the torque density improvement in terms of machine design parameters. So the machine design parameters would include the electric loading, the magnetic loading, the winding factors, and so on. We develop a relation between the amplitudes of harmonic currents to maximize torque density improvements for a given peak value of phase current. We then do a design space exploration and look at the design trends for these multi-harmonic radial flux and axial flux PM machines, and we assess the impact of using these harmonics on material utilization, losses, and torque ripple. We then demonstrate the potential to achieve 33% improvement in torque density and 65% improvement in torque-to-rotor inertia ratio compared to equivalent three-phase design in axial flux machines. So this is the first work to really show that axial flux machines can benefit from this technique. And we then experimentally validate it on a prototype multi-harmonic axial flux PM machine. In a conventional machine, if you can see the cartoon here, the air gap field has two components. The normal component Bn is due to the permanent magnets on the rotor, and the tangential component Btan is due to the stator windings. So if there are no harmonics, unless you shape the rotor to create sinusoidal field, the rotor field Bn is going to look pretty much like a square wave as shown here, whereas the tangential field ideally would be a sinusoid of just the fundamental component as shown here. But in the presence of harmonics, if we can inject harmonics with the right phase angles, we can then create a B tangential field which looks somewhat approximately like a square wave. So this has the fundamental third and fifth harmonic. So it's not yet a perfect square wave, but it's getting there. And what happens next is that we compute the shear stress on the rotor. So the integral of the shear stress actually gives us the torque. So the shear stress quantifies the torque density. And you can clearly see that without harmonics, the shear stress is much lower, and with harmonics you get a pretty steep increase in the average shear stress on the rotor. And this is basically the fundamental principle of how we are operating here. So we want to use spatial harmonics. So these are, if you see the x-axis, it's the angle, which is the spatial angle. So these are space harmonics. We want to use the space harmonics to increase the average shear on the rotor and thereby improve the torque density of the same machine without increasing critical materials. So the space harmonics basically increase the average shear on the rotor, increasing torque density. So if you look at the currents in the machine, the currents in an M-phase machine, so conventionally M is 3, but then in a 3-phase machine you do not have sufficient degrees of freedom to control the harmonics, so you need a more than 3-phase machine. So the current in phase K, so K will go from 1 to M. So in current in phase K of an M-phase machine can be written like this, where SHI is called the sequence number and AHI is called the current injection coefficient, and I hat is the peak value of phase current. So AHI is basically the harmonic current component IHI over I hat. And instead of just writing the total torque, you can write the torque per rotor volume, which basically translates to torque density, is proportional to the magnetic loading, which is B delta H hat. This is due to the rotor permanent magnets, and AH hat, which is the electric loading, and AH hat is proportional to AH, which is the current injection coefficient, times the winding factor. And for maximum torque enhancement, it is clear that the AIs or the AHs should be in the same ratio as the product of B delta and KWs. And we've introduced this constraint to ensure a fixed phase current amplitude for different values of A. So this constraint ensures that when you have harmonic injection, the net phase current value would remain the same. And this is an important parameter because the peak value of phase current is related to the saturation in the machine. So in practical multi-harmonic machines, A1, which is the fundamental current coefficient, is always greater than 1. And A3, A5 and so on can be greater than 0, and this would result in net torque density improvements for a fixed phase current amplitude. So this is basically like looking at your Fourier series. So as you increase the harmonics, your fundamental amplitude can increase without shifting the peak value of phase current. So if you look at a perfect square wave, the fundamental is 4 over pi times the peak amplitude, right? So it's beyond the peak amplitude, but then the peak of the complex current or the net summation will always remain at I hat. So first we now look at the radial flux machine design space exploration to see how the radial flux machine designs in the presence of harmonics would look like. So for this we did 2 design space exploration studies. In the first study we only had fundamental excitation, and in the second study we had the fundamental 3rd and 5th harmonic, and the winding which we designed is a 7-phase 14-slot winding which allows us to control 8-pole pair, 24-pole pair and 40-pole pair, so the fundamental 3rd and 5th harmonics. The winding factors for these harmonics are shown here, and you can see that the 5th harmonic winding factor and the 3rd are kind of low compared to the fundamental winding factor. So we don't expect a lot of contribution from the 5th harmonic and relatively minor contribution from the 3rd harmonic, so that's expected. But let's see how what kind of improvements in performance we get here. And the objectives are to maximize the torque density, maximize efficiency and minimize torque ripple. The parameters for this optimization are all the geometric parameters listed here, as well as the fundamental 3rd harmonic and 5th harmonic current ratios. So 2 studies were performed to explore the design space of a 7-phase 14-slot radial flux machine. And these are the design space exploration results. So in this plot, you can see the 3 objectives plotted, and you can really see that the circles are all the Pareto front designs from the first study where you only have fundamental excitation, and the diamonds are from the second study where you have the fundamental 3rd and 5th harmonic excitation. And you can really see that the highest torque density designs are all diamonds, right? So the diamonds have much higher. So the circles are all here, the diamonds are all here. So they are much more torque dense compared to the fundamental only designs. And you can also see that the diamonds have lower efficiency relative to the fundamental only designs. But if you look at any given efficiency, so if you draw a line like this, so for any given efficiency, the most torque dense designs are going to be the diamonds, right? So that's because the harmonics are effective in improving the torque density of the machine. So if you look at critical parameters such as the rotor yoke thickness, the stator yoke thickness and the stator tooth width, you can see that study 2 with fundamental 3rd and 5th harmonics has thinner rotor yokes, thinner stator yokes and thinner stator teeth, better utilizing the iron in the machine. So this clearly shows that the harmonic excitation better utilizes the machine and improves the torque capability, resulting in a cumulative increase in torque density. Similarly, here are the plots for torque density, efficiency, and other performance parameters, which is torque per rotor volume and torque per PM volume. You can see that the torque density on an average is significantly higher for the multi-harmonic designs. Similarly, the efficiency, although is lower, that is due to the iron losses which come in when you have harmonics. And then you can look at the torque per rotor volume, which is higher, and torque per permanent magnet volume. So these days, due to the trade wars and everything else, critical materials are a concern, and this technique really ekes out more torque from the machine for a given permanent magnet volume, and it's very attractive. So at a given efficiency, really, multi-harmonic designs have higher torque density and better utilize permanent magnets and iron. So then now we look at, how should these current injection ratios or current injection coefficients A1, A3, and A5 be? So we earlier said that theoretically A1, A3, and A5 should be in the same ratio as the product of the winding factors and the magnetic field component product, right? So what we did was we picked the optimal design from study 2, and we fixed its peak current at I hat, and we only varied the current injection coefficient, right? And we got this whole slew of designs as we varied, A1, A3, and A5, and we selected the most torque dense design. So the x-axis is the torque density. We selected the most torque dense design, and when we zoomed in on it, we plotted the PM field harmonics. So these are the PM field harmonics. The winding factors are anyway known for this machine, and what we found was A1, A3, and A5 for this design are in the ratio 1:0.248 is to 0.076. And when we look at the product of the magnetic field component and the corresponding winding factors, they are also in the same ratio. So this really validates our theory that having the injection ratios in the same ratio as the magnetic field component times the winding factor gives us maximum torque density improvement. So in summary, in the radial flux machine design space exploration study, what we saw was that multi-harmonic current injection, which is study 2, achieves higher torque density beyond fundamental excitation for a given number of phases, slots, poles, and peak phase current. Multi-harmonic multi-phase machines are more torque dense at any given efficiency compared to fundamental excitation only designs. And multi-harmonic designs show about 17.9% higher median torque per rotor volume and 15% higher median torque per PM volume, improving iron and PM utilization. And finally, we can also say that multi-harmonic machines could operate with just fundamental excitation, right? Because the torque densities are not too bad. So below rated torque conditions, you could operate them as a fundamental only machine to achieve higher efficiency, and then you could switch to multi-harmonic mode beyond the rated torque, so with reduced efficiency. So there are applications such as robotic applications or off-highway vehicle applications where you really want the torque density at transient loads, but you don't care much about efficiency under those conditions. So you could use the multi-harmonics for that boost mode, for boosting the torque density just for a short period of time. So yeah, these designs are torque dense, have better material utilization, and are particularly attractive for applications with transient drive cycles. So now we see if the same things are applicable for axial flux machines. So the axial flux machines typically have wide open slots, which are supposed to damp the harmonics and so on. So we want to see if this also applies to axial flux machines, because they are supposedly very torque dense, and can we improve their torque density even further, right? So we selected an axial flux machine which is based on a 3-phase axial flux machine that we previously designed in reference 1, and this was for an off-highway vehicle electrification application. You can read more about it in our transactions paper. And again, we repeated the same 2 studies. So study 1 is only fundamental excitation, and study 2 is fundamental 3rd and 5th harmonic excitation. The objectives were the same, and here are the parameters of the design. So we used a 2D FEA solve with a multi-objective genetic algorithm to evaluate the designs. And You can see that these are the results from the design space exploration. So the red dashed line here shows the power density of the three-phase axial flux PM machine, and this was a heavily optimized machine. The machine was extremely, heavily optimized. And what you see here is that the multi-harmonic designs are significantly power dense than the heavily optimized three-phase design, right? So it's significantly power dense. So that's an interesting thing that we find here. So it's really helping us move beyond what was capable using just three-phase design. And if you look at the slot width and the stator yoke, you can see that the slot width of the multi-harmonic design is significantly higher, which means the tooth width is narrower, because the stator is composed of slots and teeth. So if the slots are wider, the teeth are narrower. So again, better utilization of iron. And even if you look at the stator yoke, you can see that the yoke thickness is much thinner in the multi-harmonic design relative to the fundamental only design. So we see the same conclusions are valid here, where the average yoke thickness and the average tooth width are lower for multi-harmonic designs. So we selected the design and we fabricated a new stator. So the rotor was the same 16-pole rotor from the design one, which is the baseline three-phase design. And here are the parameters for the three-phase and seven-phase machine. So the inner diameter of the core was the same, the outer diameter was the same, the air gap length is different now because we optimized it to this value. The stator yoke thickness is smaller for the seven-phase machine and so on. And the efficiency was slightly lower, but then the torque ripple was significantly lower. And this could be because the machine was kind of closer to saturation, so the torque ripple was lower, or it could also arise from the winding factors because now we had very different windings on the two machines, right? So we experimentally validated on a mill. We configured a mill as a contact-free dynamometer, and we had the machine here. We had the load cell on which we would measure the reaction torque. So initially, we compared the static torques with just fundamental currents, and you can see at different current amplitudes, you can see how the torque versus rotor position looks like. And then we computed the static torque with fundamental and harmonic currents. And as expected, the fundamental is the major component. The third and fifth harmonic components are smaller. The fifth is actually very negligible because the winding factor is also pretty low. It's less than half, so it's very negligible. And so now when we compare the results from these hardware experiments on design 2 and design 1, and we also use the design 3, which is an ideal multi-harmonic design. So design 2 uses the same rotor as design 1, but in design 3, what we did was we chose the optimal value of rotor parameters from the optimization. So it would be a new rotor. We did not fabricate it in the interest of time and money as well, right? So we did not fabricate it. This is just an FEA only result. But the first two are in hardware, and you can really see here that compared to the three-phase machine, the design 2, which uses a suboptimal rotor, it still has improved torque capability, whereas if you use the optimal rotor, you achieve nearly 33% improvements in torque capability of the machine. So the torque density is also increased by approximately 33%, and the torque to rotor moment of inertia, really you see a huge improvement. You see it jump from 6.9 kilonewton meter per kg meter squared all the way to 11.3, right? So it's a huge jump in the torque to rotor moment of inertia ratio. So this is the kind of improvements we are seeing in this, and it really goes to show that multi-harmonic current injection helps improve electric machine torque density significantly. So in conclusion, electric machine torque density can be improved using spatial harmonics, and torque enhancement using spatial harmonics is applicable to both radial flux and axial flux machine designs. And we showed in this work that relative to fundamental only designs, multi-harmonic designs can achieve up to 18% higher torque per rotor volume and 15% higher torque per PM volume, and multi-harmonic axial flux PM machines are capable of achieving up to 33% improvement in torque capability and 65% improvement in torque to rotor inertia ratio. So it's well suited for transient load applications, and it better utilizes materials. So that's it for today, and I thank you very much for your attention. Thank you.